Hey everybody, here we are on 7.2 notes. This is basically the second to last thing we're going to learn in calculus. And then there's a lot of stuff we have to go over and review and touch on again. But this is kind of a fun one, I think. Basically what we're going to do is we're going to be creating solids by revolving an object around an axis. So the best way to do this is to actually show you some examples, but let's talk about some vocab first. So a solid of revolution is a 3D object made by revolving the area of something, which this area is going to come from the area of a curve or two curves, and we create an interval. That area gets rotated and it creates a 3D object. The axis of revolution is the line that we rotate about. So, for example, if I had this line here and I was rotating, let's say, this shape like this, right? I'm going to draw a little squiggly here to show which line I'm rotating. Then basically what happened is this point on here would get rotated around in a circle like such, and every single point on the circle is going to get rotated around, right, around, and basically what it's going to do is it's going to form a shape. Let me just show you with a better visual here, right? So let's pretend we have this shape and we're going to rotate it around the y-axis, right? Then what that means is watch as the shape gets rotated around, right? So it's getting rotated around that axis there and coming back to its original spot. So what happens as we do that if we draw all the area displaced as the thing goes around? So watch now, we're going to actually show you the object formed as it goes around, right? So you notice it's keeping track of the space that it displaces, and we get that, and you can see that it creates like a solid, right? In this case it's kind of like this cup shaped thing. Another way to see this is you see how it forms a circle, and that shape that you see there is actually really important for how we're going to find the volume. You see that like circle within a circle, looks like a sideways O. That shape is very important for how we're going to calculate the volume. Okay, so we can rotate along a vertical line like that. We can also rotate around a horizontal line like this. And let me just show you that real quick. Okay, so let's say we have a horizontal line like this, and we're going to rotate in this direction. And let's say the object we're rotating maybe is, I don't know, like a rectangle like this, right? Then this object will get, like each point is going to be rotated around like this, right? You're going to get it around like this. And basically what it's going to do is it's going to create this shape like such, which is in this case like a, in this case it forms like a sideways cylinder. They're really hard to draw, especially for me who's not an artistic person. And we could have any kind of line that we rotate around, but in calculus you're only going to see the vertical line and the horizontal line. And as we do this, because we're rotating it in a circle, we basically create these circles. The cross section is a circle. Okay, so a good example of this is, look at this cylinder here. If I cut a cylinder horizontally, then the cross section is this circle here, right? Like if I just cut a little slice off of this, the cross section will be a circle. However, if I do a slice going vertically, then the cross section is this rectangle here, right? It's basically like if you imagine if you ever peeled something, if I just peel off one layer on the inside, what's the shape going to be? And you can see the same thing with like a pyramid. If I slice a pyramid sideways, you're going to get a square or a rectangle. And if I slice a pyramid vertically, I end up with a triangle. Now, you don't really need to know about these right now. This triangle one does come into play a little bit later. But right now what we're doing, we're dealing with objects have been rotated. And when that happens, your cross section is a circle. So it becomes important for us to remember the area of a circle, right? So the area of a circle is simply pi r squared, right? That's going to become important later. And in this other case, where you have a circle inside of a circle, imagine that the big radius here is big R and the little radius is little r. To find the area of that, you would take the area of the big circle, and you would subtract the area of the little circle, right? That's how you're going to get the total area. And so in that case, the areas, like you could factor out a pi and just do big R squared minus little r squared. And that would give me the area of the green region there, right? You're removing the little circle, which is why it's being subtracted. Okay, so I'm going to go through some things here with you to show you why these formulas here work, and then we're going to start applying them to certain things. Okay, one example of a solid of revolution is like a vase or a vase, if you want to say it that way. As you can see here in this picture, right? Like this, you can get the general shape, like we could fit like a polynomial to it, like this curve here gives the shape of the vase, which is shown over here on the x and y axis. And to create the actual vase, we'd take this region here and we would rotate it along the x-axis, which I'm going to go to rotate it, and you can see what that looks like. Sorry, it's having a little bit of trouble. Okay, so we're sliding it, rotating it. Okay, let's try this one more time. So that has a general shape, and as we rotate it, it is going to create the shape of the vase. It's a little bit hard to see from that angle, right? But we could turn this, and so you could see that it's actually creating this 3D shape. I'll go through that whole thing again, right? If you're looking at it from like a side view, that shape is being rotated about the x-axis, and it's creating this vase, right? And the vase is a three-dimensional object. And so the question becomes, well, how do I find the volume of this vase? And with calculus, we can find the exact volume, right? Just like we can find the exact area of weird shapes, we can find the exact volume as well. And the way we do that is very similar to the way we found areas. Okay, so if you were asked to find the area under this curve, you might draw a bunch of rectangles and then add all those rectangles together, and that would approximate the area, and then we would take the limit, just like we talked about before, and as you take the limit, it ends up being an integral. So how do I find the volume if I rotate this region around the x-axis? Well, instead of drawing rectangles, we're going to draw this shape, which turns out to be a cylinder, right? Which is, if you look at it directly from the side, it looks like a circle, right? So we're gonna draw, I could draw one, and that would approximate the volume of it, but you can see it's not a very good approximation. And the more of these that I draw, the better of an approximation of the volume it becomes, right? So as you can see, when it gets really small like that, it's like approximating the volume very closely. And so basically the question becomes, well, it's like adding up all the areas of those little circles. So basically, if I can find the area of one of the circles, like what's the formula that's going to give me the area of each circle, and then integrate it, then it'll add up all the circles together, which will eventually then be the volume of this three-dimensional object, right? So that's where this comes in here. And there's two different ways we revolve, right? Sometimes we revolve around the x-axis, that's around a horizontal line, and sometimes we revolve around the y-axis, which is the one that's over here. So basically the idea is we're going to find, like, let's draw this on here. If I was revolving, let's say this thing, then it's going to be rotated, let's say, around the x-axis, right? So it's going to look something like this, right? That would be like a cone. What I would need to find is what's the radius of this cone, right? This is the radius. And the radius is determined by the function, right? The radius is the function itself. And so I would then try to find what's the area of that circle there, which is just pi r squared, which r in this case is the function. And then I would integrate that radius over the given interval, wherever you're going from there to there, and that would end up telling me the volume. Okay, so if we're going in the x direction, the important thing to notice here is all our functions are in terms of x, and the limits on my integral are x values, not y values. And then this pi over here comes from the area of a circle. We're basically using this formula that we came up with up here to find the volume. Okay, so I think this is gonna be best with like an example. So let's look at the example 1 here. We're gonna find the volume obtained by rotating about the x-axis. So you can see down here they already showing you what you're gonna rotate. Basically what's gonna happen is we're gonna rotate this piece around in a big circle. We're gonna rotate the whole thing in a big circle, right? And we're gonna rotate every point on here in a big circle. And you know, if we drew that, then we'd get some sort of shape like this that, you know, gets rotated. They're very hard to draw, but the idea is, like, you see these circles in here like this. They don't look like full circles because you're looking at it from an angle, but we need to find the area of that circle, right? So like the area of this piece that I've drawn there, it's a circle, right? It's a full circle. There's no in between piece. So the radius is simply the function value, right? That, like, this height right here is simply you know, the function value is the f of x. So what I did was already part A. I drew the radius. There is no inner radius in this case. There's only one single radius because there's no other function. So there's not going to be a little r of x. There's simply going to be a big R of x, which in this case is my function. Right? It's this function. And so to find the volume of this thing, I would integrate. I'm going to multiply by pi because that's going to be part of the area of this circle. Actually, let's do it this way first. So I'm going to integrate from 1 to 4 because those are the limits that were given to me in the problem, right? That's where the left and the right bounds are. And I'm going to integrate the area of the circle I found. And the area of the circle I found is pi r squared. But in this case, the r is simply the function value. So it's going to be pi times x squared minus 4x plus 5 squared. Right? And what we can do is, and what we'll notice as we go, is you can always just factor out the pi. That can always be brought to the outside. And, you know, just ignore it until the end. And so it's just going to be pi x squared minus 4x plus 5 squared dx. And to find the area of this thing, I would integrate this and then plug in 4 and 1, right? So I think, you know, maybe this is one we can do by hand. You could also, you know, usually this is like on a calculator section or something, so you could do it with a calculator. But let's go ahead and practice integrating. So integral of x squared is x to the third over 3 minus 4x squared over 2 plus 5x. Don't forget this whole thing is multiplied by pi, and we have to evaluate from 1 to 4. So it's going to be pi times 4 to the third over 3 minus, this is actually 2 times 4 to the third plus, that's 20, minus, plug in 1. Let's go and make this pi multiply by everything. It's going to be 1/3 minus 2 plus 5. So it's going to be pi. 4 to the third is 64. Minus 4 squared is 16 times negative 2 is negative 32 plus 20. Simplify this whole thing, it's going to be 3 plus 1/3 is 10/3. So it's going to be minus 10/3. Let's combine the piece with the thirds with this piece, and then we'll combine this piece with that piece, and then we'll combine them all afterwards. So it's going to give us negative 12 plus 54 thirds, which 54 divided by 3 is 18. So it's going to be 12 plus 18, which is 6. And then this whole thing has to be, remember there's a pi on the outside the whole time. This whole thing has to be multiplied by pi. And the units on this are cubic units because it's volume, right? So we're getting 6 pi units squared for the volume of that one. All right, the next piece we're going to do here, same idea, except let's draw this one because they didn't give us a drawing. We're going to take the function f of x equals x, which looks like this. This is f of x. And the function f of g of x equals x squared, which looks like this. We're going to take that region that's formed in between these two, and we're going to rotate it about the x-axis, right? That's what it tells us how to rotate it. So we're going to rotate it there. All right, so basically, the idea is we need to know, like, what's the shape look like that we're rotating. So since we're rotating it about the x-axis, there's going to be 2 radiuses. So if you start at the axis of rotation and just start drawing a vertical line going up, the first thing you hit is the inner radius, right, is the little r. So the first thing I hit here was the red function, which is g of x. That's my little r. Okay, and then we're going to go and do the same thing. We're going to like start drawing the line up. We're going to pass that first one, and the second thing I hit is going to be my big R, right? It's going to be the outer radius, which is, in this case, f of x, right? This one was the inner radius. This one was the outer radius, right? I can try to draw this. If you imagine, if we rotate this thing around the x-axis, right? If I rotate right here, it's going to go around like this. This one's going to form a circle like that. Maybe I can do that in blue so we can see that it's the blue one. And then the red one's going to carve out a path that looks like this. Right? And so you can see the shape that's obtained is, again, it's sideways, but it's that disc. It's a circle within a circle. Right? It looks like, let me come up here to this thing. It looks like this. And so we're going to use that formula, which is basically, we're going to add a bunch of those things together. So I'm going to take my big R, which is f of x, and we're going to square it. And we're going to subtract our little r, which in this case is g of x, and we're going to square it. Because we're creating circles, the whole thing has to be multiplied by pi. And then we need to know what are the limits of integration, right? What numbers should I put here and here? And in this case, they're not given to us, but they're at these points of intersection, which if you remember from last lesson, we find the points of intersection by setting the two functions equal to each other. And solving, so I could subtract x on both sides, and then we can factor and solve, and we'll get x equals 0, x equals 1, and you plug those in, it's going to go from 0 to 1. Those are the points of intersection. Again, they're x coordinates, right? And so there's not a whole lot of space on this one, but f of x is basically x, and g of x is x squared. And we'd integrate that. Let's do this one on a calculator. Okay, so we're just going to do math 9, integrate from 0 to 1. F of x was x, so it's going to be x squared. G of x was x squared, so that's going to be x squared squared, which is x to the 4th, dx. And something I shouldn't forget is this whole thing needs to be multiplied by pi, right? Because we're finding areas of little circles. So this thing should be multiplied by pi. And if we do that, we're going to get the volume is 0.4188 units cubed. Right? It's not a very big space. It's just a little tiny thing being rotated around. Okay, in the next example, it's a little bit different. We are rotating about the y-axis in this case, and our function is bounded by y equals the cube root of x and y equals x over 4. So it's important to identify which one's which. Well, the blue one is the line, and the red one is the cubic one there, right? So notice how they've identified that we're rotating about the y-axis, which means our axis, like this thing is gonna rotate like this way, right? Like so we're gonna rotate it going in this direction, and the shape is gonna look something like that. And there's this inner piece as well that looks like that. And this is our cross section, right? We're gonna find the area of this thing, and we're gonna integrate the area of that thing, which will tell us eventually the area of that whole piece. So to find the inner and outer radius, again, like the technique would be start at the start. I'm gonna go and erase this so we can see how this goes. Start at the axis of rotation, right? So put your pencil there and start drawing a line towards your functions, right? The first function you hit is your inner radius, right? This is my inner radius. And then if I do that same thing again, but just go past that first one, then the second thing I hit is my outer radius, right? So that's what part A is asking us to do, is find out which one's the inner and which one's the outer. So in this case, the red is the inner piece and the blue is the outer piece. So we use little r for the inner piece. In this case, it's going to be little r. The inner radius is going to be the cube root of x. Let me not write it that way. Don't write that. Let's write, inner outer is like a better thing here. So in is going to be y equals cube root of x, and the outer radius is going to be y equals x over 4. So let me redraw this thing. So the outer one creates that shape, and the inner one creates this shape, and we're trying to find the area of this piece, which is basically going to be the outer circle minus the inner circle. So I need to find the area of the outer circle, subtract the area of the inner circle, and integrate that, right? So the problem is the area here needs to be, because I'm going in the y direction, all my equations need to be written as y. So not y equals x, but x equals y. So we need to solve each of these, right? Like, so I need to solve this. Y equals cube root of x. I can cube both sides. So x is going to equal y cubed. And to solve this other one, I can multiply both sides by 4 and get x equals 4y. And those are what I'm going to use because I'm going in the y direction. And so the equation here is going to be pi times, we're going to have to figure out some points of intersection to figure this out. But basically, the area of the outer circle, which is this one, that's going to be the area of the outer circle, minus the area of the inner circle, which is, and then dy, because we're integrating with respect to y. As far as the limits of integration go, we can see that the first one is at 0. This other one appears to occur at 8, 2. However, we should just check. Let's just double check and figure out if that's what it actually is. So we're going to set these equal to each other. So I'm going to set y to the third equal to 4y. We can subtract 4y on both sides. Factor out a y. And we're going to get y equals 0. And then y squared minus 4 equals 0, which is going to give us y equals 2 and y equals negative 2, right? We're using y coordinates here. So y equals 0 is that first piece. We don't have this y equals negative 2 piece because we're not showing that on this graph. But we do have the other piece. And so what's important to note here is I'm going to write 2 up here, right? I'm using the y coordinate up here, not the x coordinate, but the y coordinate to integrate this, because we're going in the y direction. So again, we can just plug this into our calculator. It may look a little bit weird as we plug into the calculator because there's no way to use y instead of x. So we're going to do pi in the front. All right, let's just clear it. Let's start with pi. Math 9, 0 to 2 of 4. We have to use x because there's no way to put a y into this. So there's the outer radius minus the inner radius, and you could have like cleaned this up if you wanted to, like, and just wrote an x to the 6th instead of x to the 3rd squared, but I just figured I'd put it in like it is, so you could see where it's coming from, and then you press enter, and we're getting the volume here is going to be 76.595 units cubed. All right, and let's do some more.
Okay, so next we are revolving this region here, which is obtained by rotating y equals x, which is the red line, right? And y equals x squared minus 2x, which is that blue line. And we're rotating it about the line y equals 4. So we're rotating it about this line up here, right? So that's going to change it a little bit because we're not rotating about the x-axis. So let me just show you a quick demonstration of how this thing is rotated and what it looks like. I've graphed the two functions that we're rotating here. And we're going to rotate it about the line y equals 4. Oh shoot, we need to change it a little bit. Okay, we're going to try this again. So there's that region, and we're going to rotate it along the line y equals 4. And you know, we're looking at it from a certain angle, so it looks like that, but we can rotate this around and you can see that it's making this bowl-shaped thing, right? There's like the green region is the outside, and that blue region is the inside of the bowl shape, but it made a 3D object. And we can find the volume of this object by finding the volume of the outer piece, and then finding the volume, and then subtracting the volume of the inner piece, the same way we've been doing it. So basically we need to know what's the inner piece and the outer piece. So again, we're just going to start at the axis of rotation, which this time is this y equals 4, and we're going to start drawing our radius going down, and the first function I hit is my inner radius, right? So that means the red one is the inner radius, and then we're going to do it again, and we're going to just start drawing down, and the next thing I hit is my outer radius, right? So the blue one here is going to be part of my outer radius. Now, the challenging piece here is we can't simply use the function, because the function value tells us the distance from the x-axis to our function, right? Like our function value is giving us this distance that I have there in black, but we don't want that distance, right? We want basically the distance up like this, right? So we have to figure out how we find that distance, because that's going to be the radius. And so if you think about it, the whole distance from the x-axis up to this line, the whole distance is 4, right? That whole distance is 4, and we want to subtract off that black piece, which is the function value. So really our inner radius here is 4 minus our function. So our inner radius, let me write this, the inner radius is 4 minus x, right? Because again, the whole distance from the x-axis to the line of symmetry is 4, and we're subtracting off the black piece, which is created by, the function is creating that. So our inner radius is 4 minus x. Our outer radius is going to be I don't think I used the best location for this one, so let's use maybe this one over here. And that same thing happens where we're trying to find the blue piece here. The blue piece right here is our outer radius, but the function tells us this black piece, right? The function tells us the distance from the x-axis, and so for the outer radius, again, we need to do 4 minus our function to get the outer radius. Right, and now when we're doing our when we're doing the formula, remember, if we rotate this thing, it's going to look like, right, we're going to rotate this direction. We rotate the inner radius as well. And you can see, if you do that, you can see that we're obtaining this disc shape, right? Which if you remember, the area for that disc shape was pi r squared minus little r squared, right? The outer circle minus the inner circle. So we're going to do that in an integral, right? We're going to do pi, I should use a different color. We're going to do pi times the outer radius, which is 4 minus, let's go and distribute the negative, so 4 minus x squared plus 2x, that whole thing squared. And then we're going to subtract the inner radius, which is 4 minus x. And we're going to integrate this whole thing. We do need to know, the thing we haven't found yet is what are the limits of integration, right? Where do we start and where do we end? Notice everything's in terms of x because we're rotating about like the x, a line that's parallel to the x-axis, right? So we're using x coordinates. So the first point of intersection here is at 0, so the lower limit's going to be 0. And the second point of intersection up here looks like it's 3. We could double check that it's 3 by setting these two equations equal to each other. I'll go ahead and do that up here. We'd subtract x on both sides. And we get this. We would factor out an x. We get x times x minus 3, and that would give us two answers, x equals 0 and x equals 3. Right, and so that's just confirming that this upper limit is 3. Right, so now that we're there, we can go ahead and go to our calculator and see what the volume is. Actually, this is kind of cool. This calculator gave it to us, right? It's giving us a volume of 96.11, but let's just verify with the calculator just to make sure we didn't mess up our formula somehow. All right, so put it in my calculator exactly how it is shown on the paper, right? So it's pi times the integral from 0 to 3 of my outer radius, which is that function, and then minus, right, minus my inner radius squared with respect to x, and when we do this, we get 96.1327, which you can see is the same answer that the little app gave me. Alright, so we got one more example to go through here together, and then you'll practice in class. Okay, so here's another example. We're trying to find the volume obtained by rotating about the line x equals -1, so you can see that drawn over here, right? We're rotating about that line -1. The function y equals square root of 2x, and y equals x minus 1. So again, let's just identify which one's which, right? So this one is the curvy one, and the red one is the line in this case. You can see there's already a picture of what it looks like when you rotate it, but it's kind of helpful to see as you rotate what it looks like. Let's think about some things here, right? Notice how we're rotating about a line that's parallel to the y-axis. That means when I write these functions, and it's kind of given to you here, but when I write these functions, they need to be in terms of y, because we're rotating about something that's like the y-axis. So maybe something we do right away is just convert these equations to y functions, right? Meaning we have to solve for x. So let's start by dividing, let's divide by 2 on both sides, and we're going to get y over 2 equals square root of x minus 1. Then we can square both sides, and we'll get y squared over 4 equals x minus 1. And then we can add 1 to both sides, so we'll get x equals y squared over 4 plus 1, right? So that's the converted equation for the blue one in terms of y. It gives the same curve. It gives the same curve, but it's in terms of y instead of x. And then the red one's a bit easier. We're just going to add 1 to both sides, and we're going to get x equals y plus 1, right? And I switched the sides of the variables too, just so it's easier to see. And so we need to decide which one of those is the inner function, which one's the outer function. And since we're not rotating about the axis, like with the y-axis, the x-axis, there's going to be some number that we have to add. So again, to do this, it's the same idea. We're going to start at the axis of rotation, and we're just going to start drawing a line towards our function. The first function I hit is my inner radius, right? So that means the blue one is the inner, and the second function I hit is my outer radius. So the red one is my outer radius. It's kind of helpful to see if we actually sketch this thing. So let's just do a quick sketch the best that I can. I was going to rotate around in a circle. Like this. And then the inner radius also rotates around in a circle. And so we're trying to find basically the area of this washer thing here. And then we integrate the area of that washer, and it'll tell us the volume, because it's going to basically add up a bunch of these little tiny slices and then give us the volume, right? So if you look at the inner radius on that thing, it's not just the y value here, right? You can see that there's an extra little piece right here, right? There's an extra piece of 1 on that. And so what our inner radius, so let's start with the big R, which is our outer radius, right? So in this case, the big R, the function itself gives me the distance from the y-axis to the function, and then I have an extra little piece, which is an extra like unit of 1, right? So my real radius is going to be the function, which is y plus 1, but then I have to add an extra unit of 1 on there because it's the axis is shifted over 1, so we're adding 1 unit to that length. And then the little r, the outer radius as well. Let me just make sure I'm writing this right. This is the inner, and then the outer radius is, no, I messed that up. This one's outer. Right, this one's the second one that we found, and this one, the blue one, was the inner one. The inner one was the y squared over 4 plus 1. That y squared over 4 plus 1 will give me the distance from the blue one to the y-axis, and then again we need to add another 1 unit because the axis is shifted over 1 unit, right? So you can imagine if the line were at like -4, we'd be adding 4 instead of 1. Alright, so now we actually need to write the equation, right? The volume equation. So the volume is going to equal the integral pi times the integral, right? Again, we're using that formula. The volume of a disk is pi times r squared minus r squared, where, big R is the outer radius and little r is the little radius, so just 2 circles. And we're going to do the outer radius squared, so we're going to take y plus 1. Actually, we can simplify that, right? Y plus 1 is the same as y plus 2 squared, right? Because it's the radius squared for the area of a circle, minus the little radius, which is going to be y to the 4, y squared over 4 plus 2 squared. and we're integrating this whole thing with respect to y. So we have a little dy over here. We need our limits of integration, which let's look at the graph and see if we can find them. Notice it's there and there. The points are 1, 0, and it looks like 5, 4. We can verify that in just a second. But if you were just using the graph, you need to remember what am I using from this graph to create this, right? So because these things are all in terms of y, right? All the functions are in terms of y. I need to be using y coordinates over there. So I need to be using the y coordinates. So I need to be going from 0 to 4, right? And then we would integrate this on our calculator and see what it gives us. And so let's do that. All right, so I'm going to show you first what it looks like, and then we'll figure out what the volume is. So I've entered the functions in terms of y. You can do this too. So if you're ever interested in, like, looking at these yourself as you go through the homework or something, you can feel free to go to Shodor. It's just shodor.org. The link is up on top. Just follow that link. Or maybe you can't see the link. Anyway, shodor.org, and you'll be able to figure it out. So I have the functions on here. Notice on the bottom we're rotating about x equals -1, meaning it's going to rotate over here. I'm going to go ahead and revolve it, and you see it's going to revolve in that direction, and you can't really see what it looks like right now, but if we rotate it around a bit, you can see that it's creating this shape. It looks like kind of like one of those traffic cones, or maybe like a lampshade or something. And you can see the green ones on the outside, and the blues on the blue forms the barrier of the inside. It's a little bit hard to see perfectly, but there it is. We can see the volume is going to be 60.34. I guess what I want to do on this one with you is to show you how to get a better approximation. So let's go back to our calculator. Now, no matter what, the pi is going to give us an irrational thing when you multiply by this pi, right? So sometimes it's better just to not multiply by the pi, but just keep the pi there. So let's do this one together. We're going to do math 9. We're going to enter the integral from 0 to 4, and again, it's it's going to look funky, but we're going to be putting x values here, even though on our paper it says y values. We don't have, the calculator doesn't know the difference, or it can't be y values. Right, and so remember, I didn't put the pi on there on purpose, right? There is no pi on there on purpose. So if I integrate this, I get -96.8. That means I did something wrong, because volume should not be negative. Oh, there it is. I shouldn't be putting +5 right here. I should be putting +2. Okay, so 19.2, right? So like without pi, it's 19.2. So really, the volume is going to be 19.2 pi, right? And so you can see, you can get a better, maybe a better approximation writing it this way, because you don't have to worry about rounding as much. You just 19.2 times pi, and then if you did that, you get the answer that Shodor had, which is 60, which is 60 something, but the 19.2 pi is actually like the exact answer, whereas this one, we're losing some values down there because we're estimating, and sometimes it's helpful to have the exact answer because you may need to do something with it, right? So just a quick review of what we're doing, right? We're taking a curve, an area, and we're rotating it around an axis. When we do that, it creates a circular cross section. Sometimes it's a full circle, and sometimes it's a circle with a missing piece in the middle. We find the area of that piece by finding an inner radius and an outer radius. And then we use the area of a circle, which is pi r squared, right? Or the area, that's the area of a circle, or the area of a disk, which is pi r squared minus pi r squared to find the area of the shape, and then we integrate the area of that shape, which is basically going to add a bunch of those circles together. Right, it's going to add a bunch of those circles together over our interval, so it's going to add a bunch of these circles, and eventually, you know, if we add them all up, it will take up the whole space there, and it will tell us the exact volume of that entire shape. There is one other formula that I want to try to give you. Okay, it's an overall encompassing formula, so if you forget everything else, you can always, you know, go back to this formula and it will help you find it. The volume of a solid formed by rotation is going to be pi times the integral from a to b, right? We have our two radii here, so there's the first one and the second one. They both need to be squared, and this applies for dx or dy, so just no matter what we put in there. To find the radius, you can always just do the axis, whatever the axis is you're rotating it about, minus the outer function. So I'm going to write outer function. This means outer function. And then you can add the same idea here, axis minus inner function, right, where if is the inner function. And this will always give you what you need it to for these things. It'll always give you the volume anyway. Sometimes it may look a bit funky, like it's not going to work, but it's kind of finding it on the other side of the axis and things like that. What was I going to say about this? Just remember, if it's in terms of y, then the a and the b need to be in terms of y, and so do all the functions. All right, so you know, come to class ready to do this stuff.